Okay, so do you have any questions before we start? Okay. So your question, if I understood it correctly, let's suppose we have this gyroscope. So this is the suspension point. So this is our gyroscope. Let's say that there is an angular velocity in this direction. And your friend is asking, let's say that we exert a force on this gyroscope through which point? This point. There is its weight. Its weight is downward. Into the screen. The direction of the torque is into the screen. Now, you see, if it accelerates downwards, what is the direction of the angular momentum? Now, it will be in the same direction as omega. So this is also the direction of the angular momentum. It's always along the axis. Now, if your gyroscope goes down, the angular momentum, which was initially in this direction, it will be in this direction. But that means the change in the angular momentum would be downwards. But that, you see, the change in the angular momentum is always in the direction of the torque. So if the axis is to go down, we need a downward torque, which doesn't exist. The torque is into the screen. There is no downward torque. Now, suppose we exert a force on this gyroscope into the cylinder. Let's say we have the same system. There is the weight, and we exert an additional force. This is the torque due to the weight. We exert an additional force into the screen. We just push it with our hand. Now, what will be the direction of the torque? We say the torque is always R cross F. So we exert this force, let's say, at this point. So this is our R. No, the R is in this direction. This is our F. R cross F is in the upward direction. So the torque due to this force F would be in the upward direction. And if you just push this gyroscope, it just goes up, not in the direction of the force that you are exerting. Other questions? You mean this one? No, this torque causes it to go around, causes it to precess. The weight of the gyroscope causes it to precess. If we push it further with our hand, well, the weight will cause it to precess, but the force that we exert will cause it to go up. So as long as we continue pushing the end of the gyroscope, it will just precess and go up. So if this is the axis of the gyroscope, if there is only the weight, it just precesses. If there is the weight plus we are pushing it, it will precess, but at the same time it will go up, because we are also exerting another torque. The total torque acting on this gyroscope will be, well, the torque due to the weight is in this direction. We are creating an additional torque in this direction. So the total torque is in this direction. So that will be the direction of the change of the angular. No, hold on. This is the torque due to the weight. This is the torque due to us. So the total torque is in this direction. Initially, this is the direction of the angular momentum. It should change in this direction, in the direction of the torque. So this is how it would go if we keep pushing it. What is the force that is balancing the weight? Let's say forget about this push, there is only the weight, the gyroscope is processing. There is the weight that is pushing the center of mass in the downward direction. What is the force that is pushing the center of mass in the upward direction so that the center of mass doesn't go down? Well, there is this force over here, which we are not studying. Well, we are not showing it because we are talking about the angular momentum relative to that point, the torque relative to that point, so the force over there doesn't contribute to the torque. So that's why we are kind of ignoring it. But in fact, that force is the force that causes the center of mass, that prevents the center of mass from moving downward. There is that additional force. And remember, the motion of the center of mass is always determined by the total force acting on the system. So since in this system, the center of mass would be doing some circular motion, the net force acting, the total force acting on my system is towards this point. So the weight is downward. At this point, there should be a force in this direction. The vertical component should balance this W, and there should be a horizontal force which will cause the center of mass to make circular motion around that point. If there is no such force over here, if you don't hold it from here, or if this point is, let's say, frictionless so that this end point is free to move, then you don't get this precession. If this support point fixes this point, that means it's exerting a force at that point. And that force is what prevents the center of mass from going downward.
Let's assume, for example, that we have this system and then we give it a force and it starts rotating by the normal thing. Is it going to go forever or is it going to go back to the initial position after a while?
After a while, well, it's just doing circular motion. If in this system, let's assume that there is no such force, there is only the weight. So we just let it free, we fix one endpoint. So what it will do is it will just make circular motion and it will come back to the initial point. Still it is rotating in the same direction. Well, this rotation axis will eventually come to this point. At least if we can assume that it is rotating very fast, in that approximation, it will come to this orientation.
Why does that thing not happen in a car?
In a car? What do you mean it doesn't happen in a car?
The wheels, we can think of wheels as gyroscopes.
Okay. Well, let's see. Now, the car has this axis, and there are the wheels at the end. Do you drive a car? Okay. So what are the forces acting on my system? First of all, what is the direction of rotation? Let's say the car is moving into the screen. What is the angular velocity? The car is moving into the screen. So it's like this. So this is the direction of omega. Now what? Yes. This is the direction of omega. So what are the forces acting on this axis? there is the weight that, let's say, here is where is the total weight. There are the friction forces. In which direction? Into the screen. There is a friction force over here. What other forces? There is the normal force. Well, the torque is created by forces. So you first identify the forces and then calculate the torque. Now, what is the torque? Is there a net torque acting on the system? Okay, let's see. Okay, first of all, with respect to which point would you like to calculate the torque? We can choose this point, let's say, the center of mass. Well, what is the direction of the torque created by this friction force? This friction force. What is the torque created by this friction force with respect to that point? Well, let's see. This is R. This is F. R cross F is somewhere in that direction. So this will be one of the torques. Torque due to the friction force. What is the torque created by this force? Well, let's see. This is F. This is R. R cross F. It's still in the upward direction. It's in this direction. Torque due to the F prime. What about the normal forces? Let's say the friction force, the torque created by this normal force. This normal force, what is the torque created by that one? Well, this is R, this is F. R cross F. This is R, F. R cross F into the screen. So it is a torque due to the left normal force. What about this one? Let's see, this is R, this is F. R cross F is out of the screen. Torque due to the right one. Well, let's see. This one you mean?
Yeah.
Let's see, this is R. This is F prime. R cross F. It's in the opposite direction. Okay. Do you all agree now? Let's see, this is R, this is F, R cross F is in that direction. In the other case, R cross F is in that direction. Any other torques? Well, the weight doesn't create any torque relative to that point. Why is there a friction force to start with? Why is there a friction force? Let's say it's accelerating. What causes the acceleration? Hmm? Well, I mean, if this is an actual car, then the car should exert some force on the wheels, which might create a torque, etc. Or we can say that, shall we study that one, or shall we study this axe rolling down an incline? If it is rolling down an incline, then the friction force will be in the opposite direction. Now, the reason is, let's sum the total torque. Now, hold on, by the way, this is also enough. What is the direction of the total torque? Well, if we assume that everything is quite symmetrical, then the magnitudes of these torques will be equal, and the torque will be in this direction, right? So the torque is in this direction. That means the angular momentum is changing in that direction. So what will it cause this particle to accelerate or to slow down? Well, you see, the torque is in that direction, the total torque. So that means the initial angular momentum, if everything over here is correct, the initial angular momentum is in that direction. Angular momentum will be changing in this direction. So angular momentum will be slowing down. So if this is going into the screen, now hold on, there is something wrong. Now, so it will call this one, if what we have done is correct, the object is slowing down. It's not accelerating. So what did we do wrong? There should be something that we have done wrong. Friction is? So we are assuming that this car is moving into the screen. Furthermore, it is accelerating into the screen. That is what we are studying, right? So what causes the acceleration? Or did we do something wrong? So? Which one? Which contact point? No, the weight, this point is right at the center of mass, and we had already seen that the weight acts as if all the force is acting on the center of mass. So there is no torque due to the weight. Now, in this case, the car becomes important. Because if we want to create a force in this direction, the car has to exert a torque, causing the wheel to rotate faster. That will cause this friction. Without the torque exerted by the car, the engine of the car, the wheel will just roll down. It's as if it's rolling down an incline, and the direction of the friction force will be just the opposite direction. Now here we are, since we are ignoring the torque created by the car. Remember, the engine of the car should, if this car is accelerating into the screen, the engine of the car should be trying to rotate the wheels faster and faster. So the engine creates an additional torque in this direction. The torque due to the engine by some means, by exerting some force somewhere. No, in the other direction, sorry. If the torque engine cannot create a torque larger than what the friction forces has, you cannot accelerate. And that is in fact what we are finding over here. If the torque of the engine is larger than we create a torque in that direction, the total torque, so angular momentum is increasing in that direction. Angular momentum in this system is proportional to the angular velocity, so the angular velocity should be increasing. So there's no precision here. But you see, you are driving a car. It's not really a precision, but something related with the angular velocity. For all of you who have driven a car, let's say you turn around the curve. Towards the end of the curve, what do? Do you turn the wheel to the other way around, or do you just let go of the wheel? You just let it go. And the end, the wheel just adjusts itself. That is also another application of the angular momentum concepts. Because the wheels are rotating, so you are turning around the curve. At this point, the wheels have this orientation. They have an angular momentum. They don't want to change their direction unless there is a torque. The wheel is exerting that torque to change them. If you let go of the torque, the wheels has already this orientation. Just because you are going around the curve, they will not change their orientation. They will keep moving. So eventually, the car will be aligned with the wheels, and you will just go straight.
Suppose we drop this thing from where you're trying. I noticed that the friction force must still be in this direction.
So you see, it's rolling down, right? So we had seen that it accelerates slower than it would if it wasn't rolling. That is the problem we had already studied. That means the friction force is upward.
Why is the friction force?
Now you see, there are two things you can do. Let's review it. Exercise. So let's say that it is accelerating in this direction. It's rolling down. Now, one thing we could have said is that we had already calculated the system and we had seen that the acceleration, if this is a ring rolling down an incline, we said that its acceleration it would have been g sine theta if this was on a frictionless surface. And we had calculated it, and we had seen that it was actually g over 2 if it is rolling down a surface with friction. And from this, you can just conclude that the friction force has to be slowing it down, so it has to be upward. Now, another way of looking at it is, you see, we had already said that if we have an object that is both translating and rolling, you can split the motion into two. One is the translational motion of the center of mass. The other one is the rotation around an axis going through the center of mass. So let's say this object, if you just imagine an axis going through the center of mass, starts to accelerate, starts to rotate around the center of mass. What is the direction of the angular acceleration of this object as it is rolling down? Into the screen. So initially it has zero angular velocity. After some time it will gain an angular velocity into the screen. So the angular acceleration has to be into the screen. Well, it has an angular acceleration relative to this axis going through the center of mass. But if there's an angular acceleration, there has to be some torque in the same direction. And the only force that can create a torque through an axis going the center of mass is the friction force. If the friction force is in the uphill direction, in that case, the torque it creates will be into the screen. So the force has to be uphill, the friction force. So in that case, if we apply, if this is what is rolling down an incline, and the downhill means into the screen, it's just rolling like this. In that case, the friction force will be uphill, that is out of the screen. So these two would have opposite directions, and hence the torques will have opposite directions. the total torque without the torque of the engine will already be in this direction, in the direction that will be increasing the angular velocity. So it will accelerate into the screen or downhill. Let's look at some hurricanes. Now, this is one hurricane. I will ask you to compare two hurricanes. This is one of them. Just pay attention to the direction of rotation. That is what we will try to understand. Clockwise or counterclockwise? So it is rotating counterclockwise. This is a hurricane in the north hemisphere. Now let's look at a hurricane in the, this is a hurricane in the southern hemisphere.
Significantly increasing strength. Now, there is a strange aspect of this storm. We do have a high pressure system.
So what is the direction of rotation? Clockwise. This is, again, the previous hurricane was in the northern hemisphere. This is in the southern hemisphere. And here is a TV news claiming that this is the second hurricane. So what is the direction of rotation? This is clockwise. Well, this is definitely fake news. So they claim that this hurricane and this one, they are exactly the same hurricane in the southern hemisphere. Now, what we are trying to understand is what should be the direction of the hurricanes in the north hemisphere and in the south hemisphere. Now, almost all the hurricanes in the north hemisphere, they just rotate in the counterclockwise sense, whereas in the south hemisphere, they would rotate in the clockwise sense. So let's see why. So let's say this is Earth. This is rotation axis, this is the North Pole, this is the South Pole. What is the direction of the angular velocity of Earth? Toward the north, toward the south? So which means? Now the angular velocity is upward. This is the angular velocity of the Earth. Now let's just imagine we are just looking at Earth from the top. This is the direction of the angular velocity. And let's imagine a point on the equator, somewhere over here. What will be its direction of velocity? You see the velocity over here. What is the direction of the velocity at this point? This is into, this is out. So this point is this point over here. We are looking at it from the top now. On the left, we are looking at it from the side. On the right, we are looking at it from the top. So we would see the North Pole over here. This is the North Pole. What is the direction of the linear velocity of this point? It's upward. What about this point? It will also be upward. Will it have a larger speed, slower speed? It will be slower. This will have a slower speed. Now let's come back to this side view. Now this is one of the cases where we will go to a non-inertial reference frame. Let's imagine that you sit on Earth. You move with Earth. And let's assume that you sit on equator. Now the equator is hot, the north is cold. So the air, there will be winds from the equator towards the poles. And remember, this point is moving faster relative to this point. So if there are some winds from this point trying to go to the North Pole, what will be their trajectory? Will they be able to go straight to the North Pole? Because remember, North Pole is at rest. This point is already moving towards the right with a large speed. So if this wind, some atmosphere from here tries to go upward, if it tries to go straight upward, well, it already has a horizontal velocity, so its velocity vector will be in this direction. Now, if it tries to go to the South Pole, we will have a similar effect. So its velocity vector will be in this direction. So you see, in the equator, we have this hot air. Hot air will just rise and try to go towards the poles. Whereas on the poles, we have cold air. And remember, in this figure at least, the air at the North Pole doesn't have any velocity. The speed is zero. Due to the rotation there, it doesn't have any speed. So let's suppose that it tries to go down. It's cold and it will try to go, but in fact the hot air, it will just rise, leaving some empty space, empty air, empty volume below, so it should be filled. So the cold air will just fill that volume, and the cold air from the poles will just go to the north, to the equator. But remember, they are just going straight. I mean, for an outside observer, what they will see is the air will just go straight down, but Earth is rotating around it. So if the outside observer is also rotating with the Earth, what they will see is this air will just go in this area, in this direction. And in this case, it will be just like this. So this is, the velocities over here are relative to an observer that is rotating with the Earth. Remember, Earth is rotating, the observer is also rotating with the Earth. Well, let's see. The winds on the northern hemisphere, when they go up, they will always have a tilt towards the right. The winds from the North Pole that are flowing towards the equator, they will always be tilted towards the left. So they will, if you just increase these figures, what you will see is the air here in the middle, it will just curl in the counterclockwise sense. Well, a similar thing will happen on the southern hemisphere, and the air here, it will start rotating in the clockwise sense. This is why the hurricanes in the northern hemisphere, they will always rotate in the counterclockwise sense, whereas on the southern hemisphere, they will always rotate in the clockwise sense. Now, the hurricanes are large geological phenomena, but this effect you can also see for small objects also, smaller objects in smaller size. And I will send you another link where two guys, one went to England, the other one was in Australia. What they did was they just filled a pool, they made sure that the water was still, And then they open the hole in the pool at the middle of the pool, and they try to see in which direction the water rotates when the pool is being emptied. And they observed exactly the same phenomenon. That in England, as the pool was emptied, the water started to swirl in the counterclockwise sense, whereas in the southern hemisphere, it started rotating in the clockwise sense.
I didn't understand how the observer seems like that. And according to relative growth.
Let's make another plot. This is inertial observer. Okay. Now this is the inertial observer. Imagine you are in empty space and you watch Earth, you follow how the atmosphere flows. So if there is some winds from the North Pole towards the equator, they will just go straight down. Let's say initially it's at this point, and let's imagine we take successive snapshots. Initially it's in the North Pole. After some time it will move here, 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 and here. This will be the direction of the motion. Meanwhile, Earth is rotating. Let's say that initially, when you take this snapshot, there is a point right on the equator aligned with that point. Now, as you are taking more and more snapshots, this point will be moving due to the rotation of the Earth. Right? So if you imagine an observer on the equator or an observer rotating with this observer, so what you will see is at t equal to 0, this point and this point, they're aligned. At the next time, this point is towards the left of your observation point, and it moves even further left and further left. So the observer on this orange dot. So let's see. This is the observer on the orange dot. So what he will see, this is our orange dot. He's always at rest, according to him. Initially, this point is completely aligned. After some time, it is towards the left. It is further left and further left. So this is why this orange dot, what he will see when he observes the motion of these air molecules over there, of that wind, this will be the velocity vector. And when he looks at the wing going upward, you see, for an outside observer, inertial observer, what happens is, you see, there is this, let's say, some mass of atmosphere. It already has a large velocity towards the right. So let's say if the wind is blowing toward the north, so it will have a northward component of the velocity, also a rightward component of the velocity. So his velocity, when it starts to flow toward the North Pole, the velocity vector of some mass of atmosphere over here will in fact be in this direction. This is for an inertial observer. Now, of course, if you move to this orange dot, what he will see is that it is still somewhat tilted towards the right, but not as much. Because due to this rightward component of the velocity, the mass of atmosphere will move towards the right. Our observer is also moving towards the right. So it will be more or less like this. Now, it would have been better if you put an observer over here, not on the equator. So this is what you would observe if you rotate with the Earth. And this is if you don't rotate with the Earth.
Last thing that you said, the equator for an observer that's in the origin.
No, sorry, for this one, the correct one would have been, it is straight up. Yes. Because the rightward component of the velocity of this mass of atmosphere is the same as the rightward component of the velocity of this orange dot. Any questions? Yes.
Bahsettiğiniz havuzu darbedeliğine ekvatorun tam ortasına yaparsanız.
It doesn't rotate. Well, when I was a small kid, there was a Turkish program of Barış Manço who actually did the experiment on the equator. He was right at the equator, the water didn't rotate. He just took one step to the North Pole, the water rotated in the counterclockwise sense. He stepped one step to the South Pole, and the water started to rotate in the clockwise sense.
Other than weather conditions, tornado equator. A tornado on equator.
Well, the tornadoes, they tend to move. They don't stay on the equator. We don't have any observation about that.
There is not any.
I mean, they tend to move either toward the North Pole or toward the South Pole. They don't stay on the equator. Because of these temperature differences, the water will move towards the poles, the atmosphere. Well, there's another consequence of this rotation of Earth. So let's say this is the North Pole, and on the equator, you just take a very tall building, and just from the top of this tall building, you drop an apple. You go to this skyscraper, this is exaggerated, you just drop out some stone down the skyscraper, so where will it fall? Will it fall straight down or further away from the skyscraper? Or will it hit the skyscraper as it's falling down? Ignore air. It will go straight down. Yes? Further away. So how many of you think that it will go straight down? Okay, let me just put these points. This is the point A. Let's say this is the point B, this is the point C. Will it fall at the point A, will it fall towards the point B or towards the point C? So how many of you think that it will fall towards the point A? You are an outside observer, an inertial observer. Well, it doesn't really matter because these points A, B, and C are fixed on Earth. For an outside observer, these points A, B, and C, they are also moving. For an observer sitting on Earth, these points A, B, and C are fixed. But the final conclusion is independent of the observer, because when it falls down, it either falls on A or towards B or towards C. So you cannot change it by changing your reference frame. So how many of you think it will fall at the point A? This point A is on the line connecting that point to the center of the Earth. How many of you think that it's B? And C? Okay, so let's see. A group? Here is the B group. And the C group. The first two rows are the C group. And after this exercise, you can take your third quizzes. A group, B group, C group. Okay, everybody should choose their sides. A group, B group, C group. Okay, why A? Why A?
Because we're on the initial frame of reference, that's why.
So?
We're observing from outside.
Okay, so? He didn't like your answer.
Yeah, it's because the star is also turning with the Earth. So when we rocket, it's still going to be turning with the Earth, but it's still, atmosphere, so it's going to be revolving around.
Okay,
It's
so
going to be a very, very small displacement, so it's going to just fall straight to the
Still,
time.
even if the skyscraper was really tall,
well, let's just imagine that the height of this skyscraper is equal to the radius of Earth.
Oh, that's a
still it's A.
So it's A. So what your claim is that if you just leave it, the Earth is also rotating, just like your rock that you are dropping, so it will just fall straight to the point A. That's what they claim. Why B? Or what's your opposition to their explanation? If you can change your sides. If you change your idea, you can just go to that group. The same holds for you. If they convinced you, you can go there. Why B?
Initially, the apple has a larger tangential velocity than the point B.
Okay.
And if we ignore the air friction, so it should go farther away from the A.
So what they claim is that initially, since our mass apple is at the point at a larger distance, it has a larger tangential velocity, which will always stay the same. It has a larger tangential velocity than the point B. So this mass, as it's falling down, it will cover a larger tangential distance than the point A. So it will fall towards the point B. So is that your explanation? Why C? Okay, what do you think? Which side do you agree?
I thought that the Earth is rotating.
Yes, everything is rotating. The Earth is rotating. The skyscraper is rotating. The mass, initially you are just holding it on the skyscraper, so it has zero velocity relative to the skyscraper.
The apple loses some angular kinetic energy, so as it goes down, there must be some kind of force acting.
Well, there is only the gravitational force which is pulling it towards the center. There is no other force.
Doesn't the velocity reduce, like the upwards? The velocity is going upwards.
Okay.
When it hits the bottom, it is reduced, so the acceleration should be towards the C.
So you are saying that when it is on the surface, its speed is lowered, so it should have some acceleration towards the C. If it has an acceleration towards C, so it will fall towards the point C.
We know that the angular momentum is conserved. So as it gets closer to the center, R will get less, I will get less, and omega will rise.
So your friend is saying if you just look at this point mass after it is released, the only force is the gravitational force towards the center. So if if you calculate the angular momentum and the torque relative to the center, the angular momentum will be conserved of this point mass only. And since it's getting closer, its moment of inertia is getting less. If the moment of inertia is getting less, its angular velocity will be getting larger. Since its angular velocity is getting larger, this point mass will cover a larger angular distance than the point A. So hence it will move towards the point B. No, this is the north. No, the point B. No, you see, we are looking from the top. Everything is on the equator. This is the North Pole. This is the angular velocity. So if you agree with them, you should go there. You are losing.
I'm still not sure.
Angular momentum shouldn't change. It's the same place.
You are saying that angular velocity is conserved. Well, mainly your idea also. The angular velocity is conserved. But you see, he also says that angular velocity is conserved. And he says that it should go towards C. You are saying angular velocity is conserved, so it should fall straight to A from the same arguments.
Can we just go sit down? I don't have an opinion. Can I go sit down?
No. Anybody else? I mean, you should also try to convince them. You shouldn't just sit there and relax thinking that you are right. Yes?
Okay.
You are C or A or B?
C.
C, okay.
No exact. But I've tried that, not experimental, but just for fun. And if you drop something from that tall, it never goes. It always hit the building.
It always hit the building. Okay, so there is an experiment over there. Yeah, that's the complication.
I don't think it's.
How high was the building?
Really high.
Really high, okay. 100 meters.
I'm going to say where I'm confused. When we drop the ball from the top of the building, I completely agree with them when they say the linear velocity must be greater at the top because the building is very tall. But what I can't quite just remember why it loses that linear velocity when it goes to point A, because I think it has to go to A.
So why does it lose the linear velocity?
Why should it? I say no. They say they shouldn't. They say that it shouldn't. I say that it should, but I don't have a reason for it.
Ah, okay, so you cannot support your idea.
Yeah.
You believe that it will fall to the point
I
A.
was actually asking you.
I will answer later on. Anybody else? Would you like to convince them? I mean, there are still a lot of people over here who don't believe in your explanation. And do you want to have some supportive explanations for your choice? Okay, you lost one more. So why do you think that angular velocity is conserved?
Because the building is on Earth, so it's connected to the Earth, and we can imagine that the highest part of the building to be another circle, but it's going to be the same. It's going to be the same. Imagine this, for example.
But you see, there is one problem though. This mass is not connected to the Earth after you drop it.
But we are going to drop it from there.
Okay? Initially, its initial angular velocity is the same. Nobody disagrees with that, right? Yeah. The initial angular velocity of this mass, at the moment that you drop it, it will be equal to the angular velocity of the Earth. The question is, what happens afterwards?
As a building is on the equator?
It's in the equator. Let's simplify it. Well, you see, the crucial thing is the distance, the change in the distance is proportional to the height. So if the height is just a couple of meters, you don't see anything. But if the height is like proportional to the radius of the Earth, then you will see a significant effect. Still, why do you think that the angular velocity is conserved? Well, the same holds for your explanation, because we always said that, okay, this point has the same angular velocity as this one, so this point has a smaller relative linear velocity, linear speed. But the problem is this mass is not connected to the Earth afterwards. So when it falls down, just before it hits the ground, it shouldn't move with the speed of this point. So its speed can be different. In fact, if you just look at the forces acting on the mass, the force is always towards the center. So there is no force in the tangential direction. The tangential component of this, the speed of the velocity of this mass will never change. It will always stay the same. It will go to B. It will have a larger tangential velocity than the point A, so it will be moving towards the point B. Or you can take the argument of the conservation of angular momentum. Not the angular velocity, but the angular momentum is conserved. But the object is moving closer to the center of rotation, and hence its angular velocity should be larger. If the angular velocity is larger, it will cover a larger angular distance than the point A. Because the angular velocity of the point A and the top of the building, they are equal. But as this mass is falling down, initially it had the same angular velocity as the point A. As it is falling down, the angular velocity gets larger, not because of any force, because of the conservation of angular momentum. Its angular velocity gets larger, and hence it will cover a larger angular distance than the point A. That means it will fall towards the point B. Okay, you can go for a 10-minute break.
You're wrong.
Yeah, you were on too, so
Yeah, that's why I changed my idea.
you changed your idea because you didn't